In this video, I'm going to talk about common factoring, which is a little bit more often known as just factoring, and we're going to take it slow. This video might seem a little bit longer than the others. It's a little jam-packed with material, and it does require your knowledge of multiplication and division. Dun, dun, dun. So let's talk about a recall here. I love starting my stuff with recalls. What is a factor? And I'm actually going to not talk about math right now. I'm talking about the factors in our everyday lives. So I've got an example here. I've got a factor. If you miss a lot of lessons. So let's just package that as one thing, missing a lot of math lessons. That could be a factor that would have a result on your life. And it might not necessarily be that bad if you miss a lot of lessons. Perhaps you've done really well in math class before, you just pick up on it really well. But if we multiply that or combine that with another factor, so we'll just call this a multiplier, with another factor that you don't do your work, you don't do your homework, you don't practice, and ultimately you just don't care about math at all. If we combine those two things, we get a result. And the particular result that I'm talking about is that your mark will suffer. And so we can compare that to a math question. So if I have a factor, for instance 2, and I multiply that with another factor, for example 3, we get a result, and the answer in this particular example is 6. And so these two factors multiply together to make a bigger item or bigger number that is the result. So we're going to put that into practice with mathematics, and we're going to start by coming up with the factors that combine to make the number 18. You've probably done this before. You made factor trees or something like that in previous math courses. So this is just a continuation of a recall. So we know the factors are 1 and 18, but that's kind of boring. So let's list the factors that make 18. Well, we know 2 and 9 make 18. We know that 3 and 6 make 18. And these are all of the different factors that combine to make 18. And in fact, we can start splitting some of them up. We know that 9 is made up of 3 times 3. We know that 6 is made up of 2 times 3. So we do have some repetitious factors. We don't need to list them again if they're already here. We already had a 2, we already had a 3. We don't need to worry about these ones. So the factors of 18 are 1, 2, 3, 6, 9, and 18. So what we're going to be doing is we're now going to talk about what if there are two numbers, how do we compare their different factors? But first, we got to talk about the real life scenario, the comparison to real life. So if we talk about common factors, that's a fact or a number that two different results have in common. It's something that they share. So in my example here, we've got a red-haired male. Let's jot that down as variables. So a red-haired male, RHM, with glasses. All right, so with glasses, that's a G. And then we have a different person over here. We've got a brunette female, so BF, with glasses, BFG. There you go, BFG. So a red-haired male with glasses, brunette female with glasses. So what do they have in common? Well, the only thing they have in common is that they both wear glasses. And so that is the common factor between these two people. The common factor is that they both wear glasses. And if we wanted to write this as a math question, we're going to see this a little bit more later. I'll do this one in maybe an orange or something. So if I had the redheaded male, I'll just write R for redheaded male with glasses, plus the brunette female with glasses. I can package that together. I can say, okay, I've got a redheaded male, I've got a brunette female, and they both wear glasses. Right now, this either makes sense because, oh yeah, okay, glasses is both redhead male and female, or they both have glasses. It's just a short way of saying that these two people both wear glasses. Or this might be a little bit confusing for you. You might be wondering, where did the G go? So hopefully the rest of this video will make sense of that. Okay, so let's get back to the actual math. Forget redheads with glasses. What factors do 12 and 13 have in common? So in order to figure this out, you might have to list the different factors. So, 12 is made up of 1, 2, 3, 4, 6, and 12. And then the factors of 30. 1, 2, 3. Is 4 a factor? No, it's not. 5 is, 6 is, 7, 8, 9, 10, yes. And then 15. And then after that, 30. So what we're going to do is we're going to try to grab the common factors between these. So I see that 1, 2, and 3 are common. So those are common right there. And 6 is common right there. And that's about it. So the common factors are 1, 2, 3, and 6. Okay, so these are the common factors for those two numbers. Now, common factors are all well and good, but we don't really always want to list all of the factors they have in common. What mathematicians are really interested in is which was the greatest common factor. So that would be the most shared facts or the largest shared facts between items, scenarios, or terms in mathematics. So if I go back to this previous example, the greatest common factor, or GCF, in this example was 6. That is the greatest common factor. So let's go back to my people with glasses and hair colors here. A red-headed male with glasses and a red-headed female with glasses. So she's no longer brunette. She dyed her hair. What do they have in common? Well, they have red hair in common. So if I wanted to, I could say, okay, they both have red hair. But they also have glasses in common. So if I want to say their GCF is red hair and glasses. And then what I can do is I can say, okay, there is a male and there is a female, and they both have red hair and they both wear glasses. This part right here, the RG, that is the greatest common factor. The greatest common factor. Lots of letters on the screen here. So let's take a look at that with some numbers. Really quickly, what is the GCF, or greatest common factor, between 24 and 32? Now, because this is a video, you have the opportunity to pause it. So take a second, pause this, and try to answer all 4 of these and see if we get the same answers. Okay, so the GCF between 24 and 32. You need to know the factors between these. It's not 12, it's not 6. In fact, the GCF between these is 8. So 8 is the largest factor. You can't go 16. 16 doesn't go into 24. 12 doesn't go into 32, like I already mentioned. So 36 and 54. Now 36 does not go into 54, so that doesn't work. 12 goes into 36, but not 54. 6 is kind of small. Does it work? Yeah, but I figure there's got to be a bigger one. And there is. The GCF between these two is 18. 18 goes into both of these, and it's the largest factor for both of these. Now, what about this one? There's no constant values here. This is 2 variables, x to the 7 and x to the 4. Let me write out x to the 7 real quick. So that's x to the 7, and x to the 4 looks like this. All right, so what do we see? Well, we see a bunch of factors. This is an x times another x. These are all different factors. There are 7 of them here. There is a bunch of x's being multiplied times each other here. There's 4 of them. And so if we consider that we can combine these into their own things, I've got an x to the 4 right here. So this is essentially x to the 4 times x to the 3. And this right here over on the, x to the 3. And this right here on the other side is itself x to the 4. And so that's what they have in common. The GCF for these 2 particular items here, or the greatest common factor, is x to the 4. Now, what about this 9x to the 3 and 24x? Well, what we're going to do is we're going to deal with the number first, the coefficient on both of these values, and then the variable. So the GCF between 9 and 24, you may have already gotten it, it's 3. 3 times 3 is 9, 3 times 8 is 24. Now what we're going to do is deal with the variable. The GCF between x to the power 3 and a single x, which is essentially x to the power of 1, that GCF is x. And so the GCF between these two is simply 3x. Okay, now what we're going to do is we're going to compare GCFs and common factors to actual algebraic statements. So first we'll do a little recall here really quickly. We're going to expand this out. So let's multiply the 3x into this bracket, but I'm not going to actually do the multiplication yet. I'm going to write it out like a multiplication. 3x times 2x squared plus 3x times 5. So that's 3x times 5. Now take a look at what we have here. We have a multiplication here and a multiplication here. And that means that 3x is a factor for this multiplication question. So is 2, and so is x squared. And on this side, we have 3x times 5, so 3x is a factor of this multiplication. Let's complete the expansion. So we get 6x to the power of 3 plus 15x. But what if we were given this as the beginning of the question, 6x cubed plus 15x, and asked what the GCF is? So because we already know the answer to that, it's right in our face, that one's easy, but what if we didn't know the answer? So we'd have to be very good at division and multiplication to figure that out. And that's what we're going to practice right now. So we're going to factor this statement. So factoring is the exact opposite of distribution, which we call expand and simplify. So if this statement here, 2x plus 4, already was expanded and simplified, it was already expanded, we need to factor it. We're going to go backwards. What we're going to do is step 1, we're going to find the GCF of these two items. Now I created this question in a simple manner to make it easy. 2x and 4 have a simple GCF. The GCF is 2. Now, if we were to factor that 2 out, which is another way of saying divide, if I was to divide the 2 out of these two terms, what would I get? Well, 2x divided by 2 is simply x, and 4 divided by 2 is 2. And so this is the factorization of the original statement, 2x plus 4. Meanwhile, 2x plus 4 is the distributed version or expanded version of 2 times x plus 2. So they go forward and backward, forward and backward. We can expand to get 2x plus 4 and factor to get 2 times x plus 2. So let's try it again. We're going to get progressively more complicated. So we've been asked to factor this algebraic statement. So we've got coefficients, variables, and a negative sign. So first things first, what's the GCF? So the GCF between 6 and 3 is 3. And the GCF between x squared and x is x. So now what we're going to do is divide that out. 6 divided by 3 is 2. X squared divided by x is simply x. And so off to the side here, x squared divided by x, we're going to subtract our exponents, and so we get a single x. Now we have a negative 3x divided by 3x. So negative 3 divided by 3 is negative 1. X divided by x is also a 1, and if I really wanted to, I could write that it's times 1, but there's really no need to write that. 1 times 1 is 1. And so this is the factorization of this statement, or of this algebraic expression. If you wanted to check the validity of your answer, you could multiply it back in to check to make sure you get the same beginning statement. But writing out the expansion of it really doesn't make any sense. We were asked to factor it. Now, what if the 6 was negative? So I'm just going to write this statement again, negative 6x squared minus 3x. So what if that was also a negative? We can take negatives out as well. We can factor negatives out. And so the GCF between them now is not 3x, it's negative 3x. They both have a negative in common. And quite frankly, even if the interior here was positive, we would still take out a negative 3x because mathematicians pretty much always take the sign that leads the statement. So that sign there, if that's the beginning of the algebraic statement, we're going to take that as well. So we're saying that we're going to factor the negative with the 3x. And what we'll end up with is 2x, just like we did before, because negative 6x squared divided by negative 3x is 2x. But the positive 3x, the sign changes and becomes negative 1. So we end up with the same interior, but the negative on the outside here is still a negative. Now, if we ended up with, say, if we started with the 3x here, then the inside of my bracket here would have to switch signs. Negative 3x divided by negative 3x is positive 1. Of course, this lesson does require you to be very good with positives, negatives, multiplying, dividing, adding, subtracting like terms. It does require all those previous skills, and that's sort of one of the detriments of mathematics is that it builds on itself. So if you're not that great at those previous skills, you might want to practice those first. All right, last example for my video. We're going to try and tackle this monstrosity, and it looks horrid. When students see, or anybody really sees a statement like this, they tend to break down. They go, okay, that's too complicated, it's too hard, I'm not going to do it. But I want to show you how easy it actually is. We're going to take it step by step, coefficients first, then variables. We're going to figure out the GCF. So what is the GCF between negative 9, 12, and negative 6? Well, quite frankly, we're not going to worry about the negatives and positives. The first term is negative, so I'm going to be factoring out a negative. So the GCF between 9, 12, and 6. Again, this is a video. You could pause it and try this on your own. The GCF is 3 for those numbers. Now, what is the GCF between x4, x3, and x2? Well, we can only take a maximum of 2, so I have to say that that's my GCF for that particular variable, is x squared. Similarly, with my y's, I've got a y to the power of 4, a y squared, and a y to the power of 3. The maximum there is y squared, just as it was with the x's. As a matter of fact, I'm starting to regret making it the same. So let's just change the question real quickly. I'm going to change this to a 3, and we'll change this to a 5. All right, so now the GCF between the y values is no longer 2, it's 3. So let's just do that, y to the power of 3. Okay, so that was the GCF portion of it, but now we need to actually divide that out. So negative 9 divided by negative 3, that's positive 3. X to the power of 4 divided by x squared is x squared, and that comes from our exponent laws. X to the power of 4 over x squared is x squared because we subtract the exponents. Y to the power of 4 divided by y to the power of 3 is y. Now we'll deal with the next term, the middle term here. Positive 12 divided by negative 3 is negative 4. X cubed divided by x leaves us with a single x. And again, that's exponent rules, subtracting your exponents. Oops, that's an x squared. There we go. And that leaves us with x. Y to the power of 3 divided by y to the power of 3. Let's think about that for a second. Anything divided by itself is 1. If I had 7 divided by 7, you would say that that's 1. If we subtract our exponents, we get y to the power of 0. And in fact, anything to the power of 0 is 1. And so really, that's just a 1. I don't need to write times 1 though. It doesn't do anything. So we just leave it. Negative 6 divided by negative 3. Well, that's positive 2. X squared divided by x squared is 1. So I could write it, but I'm not going to. Why would we bother? And y to the power of 5 divided by y to the power of 3 is y squared. And we've done it. We've tackled this monstrosity. And I went really fast, and I'm sure this is a little bit complicated for some people. So slow it down, take it step by step, rewind the video when you need to, and try to listen to what I've been saying. Check some other videos. There's a wonderful Khan Academy playlist on this topic, and I hope that this all made sense. You're welcome to contact me, leave comments in the video, subscribe to my channel for more videos that I'll be making, and definitely practice, practice, practice.